Hello students, my name is Professor Urvish Mewada. I am HOD Electrical Department, Sri Swaminarayan Institute of Technology, Bhat, Gandhinagar. I am the subject matter of Power System 2 subject, which is in the 5th semester Electrical Engineering, and GTU subject code of this subject is 3150911. Students, we are currently discussing the chapter number 4, Symmetrical Fault Analysis, in which today this is our lecture number 3, in which we are going to discuss the topic number 11, the example based on the chapter. Students, in last lecture, lecture number 5, we have discussed the topic number 9, that is algorithm for the short circuit study, and in which we discuss n bus system under steady load and the network of system for computing post fault voltage and uh, means the equations for the voltage for post fault and pre fault voltage condition of the power system. And in the lecture number 5 also we have discussed the topic number 10, that is formation of Z-bus formation using step-by-step method, in which we have did certain modification in the power system and we determined the Z-bus related to the given system. Students, in last lecture we have finished all the theory portion of this chapter. Now in this lecture number 6, the last topic of this chapter is example based on the chapter. So let us discuss the example related to all the topics that we covered in the uh, all the lectures that we discussed in the previous lectures. So let us discuss with the example number 1. The data which is given is figure below, which shows the single line diagram of three-phase system. So in this system we are having two generators, so A and B both are generating sources and both are connected with a link, and a load which is delivered to this line on which we are having a fault. So the percentage reactance of each alternator is based on its capacity. So the percentage reactance that we need to determine of the particular generator, and find the short circuit current that will flow into the completer 3, means 3-phase short circuit at fault point F. So at this point we need to find out the value of the short circuit current. So in the diagram, let us discuss first the diagram. So over here we are having a generator having 15,000 kVA, and the generator number B, it is 20,000 kVA, and this is the link having the line voltage, that is 12,000 volt, and at this point we are considering the fault. Now let us the base kVA that we have, that is 35,000 kVA. So the how we determine this base kVA, the addition of this the two kVAs of means both the generators, so 15,000 plus 20,000 means the base kVA of this system is 35,000 kVA. Now let us determine the percentage reactance of the system. So as we already discussed, that percentage reactance of the alternator having the equation is the tolerance, that is 30%. So it is 30 into the base kVA, that is 35,000, divided by the kVA rating of the particular unit, means the reactance that we are finding of the particular unit. So the 15,000 kVA is of the generator A, so that's why it is 15,000 kVA. So XA is equal to 70%, and then after the percentage reactance of alternator B, so let us put the percentage value, that is XB is equal to 50 multiplied by the 35,000 divided by 20,000, so that is 87.5%. So in this diagram we are having a printing mistake, that is over here, that is this is a 50%. Now the line current corresponding to the 35,000 kVA base at the 12 kV is, we are having an equation for Vi is equal to, means P is equal to root 3 Vi cos phi. So we are putting that values over here. So I is equal to, this is the base kVA 35,000 kVA, so it is multiplied with 1000. Now it is multiplied with root 3 into the voltage rating, that is 12,000 volts, so it means 12 into 1000. So when we solve this, we will get the value of the line current corresponding to the 35,000 base kVA for 12 kV line is the 1684 ampere. Now let us solve this reactances. So the total percentage reactance from the generator, that is having neutral up to fold point F. So this is the line which is common in both the means both the generators, having the reactance that we already calculated over here. So XA is equal to 70% and XB is equal to 87.5. so from that we have drawn an equivalent circuit of the given system. Now the percentage means X is equal to the total percentage reactance is equal to, here both the inductors means the reactances are in parallel, so that's why XA parallel XB. So when we solve this XA parallel XB, we are having a value of 38.89%. so this is the total reactance of the given system. So reactance diagram at 35,000 kVA, the total reactance offered by the system is 38.89%. Now short circuit current ISC, we are having an equation of this. IS is equal to I into 100 divided by percentage X. So now we have the value of percentage X. So just put the values of the values that we already determined. The value of I means the line current is that we determined is 1684, and the percentage X that we have determined from this 38.89. so by putting the value, we will have the value of ISC, that is short circuit current at this particular point where the fault will take place. At that point the short circuit current is I is equal to 4330 ampere. So this is how we can solve the example related to the means given system. Now let us discuss the example related to the other topics. So in this system, the example number 2, the data given is for the given circuit in this diagram. So in this diagram we are having two generators. The generator G1 is having 10 MVA 0.1 pu, and this G2 is having 5 MVA at 0.075 pu, and this both generators are connected with a transformer having the base MVA, that is 15 MVA at 0.06 pu, and this is the line and which is connected with this Q. This is the point P where the fault will take place, and the impedance is 5 plus j 20 ohm, and the base kV, that is 33 kV. So we need to find the fault current when the system is unloaded and when the fault occur at terminal P. So we are having two points where we are considering the effect of fault. So this is the point where the fault will take place initially, that is P, and this is the second point where we need to calculate the effect of fault. So the fault occur at terminal Q. So let us solve this example and that will be more clear to you. Now selecting base MVA, that is 10 MVA, we need to select the highest value of the MVA and we can calculate the example related to the given system. So selecting the base MVA, that is 10 MVA, and the base kV, that is given over here of the line, that is 33 kV. So for the generator G1, let us calculate the new PU reactance of generator G1, that is X PU old into base MVA new divided by base MVA old. That this is the equation that we already discussed in the impedance section. So this is the XPU old. So XPU old of this G1 is 0.1 pu, and the base MVA of this unit is 10, and the new that we have selected, that is 10 MVA. So after solving this, we are having the new PU reactance for G1 is 0.1 pu. Now for the generator G2, mm, then the new PU reactance G2 is equal to, the equation remains same, XPU old multiplied by base MVA new divided by base MVA old. So XPU new, that is the XPU, that is 0.075 of this given system. Over here you can see that this is the XPU old, and the base MVA new, that is that we have selected 10, and the base MVA of this generator G2 is 5 MVA, sorry. So after solving this, we will have the value of C2, that is 0.15 pu. Now let us calculate for the transformer T. Now new pu impedance of the transformer T is having 0.06, that is given over here, 0.06, and the new MVA that we have selected, that is 10, and the old one is 15. So the new pu impedance of the transformer is 0.04 pu. Now let us solve this for the transmission line also. So Z base is equal to, this is the equation for Z base. Z base is equal to base kV square divided by base MVA square. So that we have already the value of base kV, that is 33 kV from the given diagram, and the base MVA that we have for this line is 10. So that we have taken base MVA, means we have selected over here, so that is 10. So by putting this value, we will have the value of Z base, that is 108.9 ohm. So this is how we can calculate all the impedances and reactance of the system. Now ZPU is equal to actual impedance divided by base impedance. So we have the actual impedance, that is 5 plus J20, which is given in this diagram. So this is 5 plus J20, and the new, that is the base impedance, that is 108.9, that we have calculated from this. So after solving this, we'll have the ZPU, it is 0.046 plus J 0.18366. So from this above data, the reactance diagram is drawn. So this is the reactance diagram of the given system. So G1 G2 is having the reactance is 0.1 and 0.15. This is the line having the reactance 0.04, and this is the point where initially fault will take place, P, and then after we have the transmission line, that is 0.046 plus J 18366, and this is the point Q where the fault will takes place, means the second point where the fault will take place. So let us discuss the case number 1. So three-phase fault occur at at point P. So we are considering this point, and where we are calculating the effect of fault current. So ZF, the impedance at fault is 0.04, that is in series with this two parallel reactances. So J 0.1 parallel to J 0.15. So after solving this two, we'll have the value of ZF, that is J 0.1 pu. So this is the value of ZF where point P where the fault will take place. Now the short circuit MVA fed into the fault, that MVA at short circuit. So base MVA that we have selected 10 divided by the PU impedance up to the fault point, that is 0.1, that we have calculated from the previous slide. Now the fault current IF is equal to, we have the equation IF is equal to MVA into 1000 divided by root 3 into kV, that we have already discussed. There V over here V in is in kV, so MVA is 100 that we have calculated from this, and 1000 means it is 10 raised to 3, and root 3 multiplied by kV rating of this line of transmission line is 33. So the fault current is 1749.5 where the initially fault occur at point P. Now let us discuss the case number 2. So in this we have the this two means generators which are in series with 0.04 and 0.0446 plus 0.183. So when the fault occur at point Q, the value of PU impedance means ZPU up to the fault point Q. So this is the point where we are considering the effect of fault. So ZF will become, we have the two reactances, both are in series, and having two reactances both are in parallel. So after solving this two, will have the ZF in terms of R angle theta, that is 0.2874 at angle 80.79 degree. Now from that, the short circuit MVA fed into the fault, that is the selected base MVA divided by the ZF, means ZF MVA, that is 0.2874. so total MVA of the where the fault take place at point Q is 34.79. now the value of the magnitude of the fault current can be determined from this equation that we have already discussed in case number 1 also, that is MVA into 1000 divided by root 3 into kV. So that is 34.79 that we have already calculated from over here. It is multiplied with 1000 and root 3 multiplied by 33. So the fault current at the point Q, where the level of the fault current is 608.8 ampere. Now assuming that the system is on the load and we are having the ES is equal to source voltage is equal to 1 pu. So for three phase fault at point Q, so we have this equation Z is equal to V upon I. So IF at means current at fault per unit is equal to, from that we can write the equation Z is equal to V upon I. So I is equal to V by Z. So V is considering over here, that is V is ES, that is source voltage, divided by Z pu. So source voltage is taken as 1 pu, so divide by 1 pu divided by Z pu. So that we have already derived over this 0.2874. so IF full current means per unit is 3.4795. so this is how we can solve the example related to this. And then after, the base current IB is equal to that is the nothing but the equation, that is root 3 VI cos phi. So the value of the base MVA that we have selected, 10 into 10 raised to 6 divided by root 3 into the base kV, that is 33 into 10 raised to 3. so from that, the base current IB is equal to 174.95. so from that, the actual means fault current is a combination or a multiplication of IFPU into I base, I base. So IFPU is 3.4795 and I base is 174.95. so when we multiply both together, we will have the actual fault current, or we can say the combined effect of fault after means the fault will take place at point P and as well as the point Q. so the actual fault current, magnitude of the fault current is 608.738 ampere. so this is the actual fault current that we can determine from the given system. Now let us discuss the example number 3. So over here, the two generators G1 and G2 are rated 15 MVA 11 kV and 10 MVA 11 kV 10 MVA and 11 kV respectively. Both are connected with a transmission line, and the generator are connected to transformer, which is shown in this diagram. Calculate the sub transient current. So once the two fault will take place, the sub transient current will increase. So we need to calculate that sub transient current in each generator when the three phase fault occur at the high voltage side of the transformer. So this is the high voltage side. Here we are stepping up the voltage from 11 kV to 66 kV. so this is the high voltage side. So that's why we need to calculate the three phase fault which means the three phase fault current level or at this side of the transformer. So let us solve this example. So the solution, the base MVA that we have taken, that is 15. so the highest MVA we can take for the solution, so that is 15. And for the generator, this is the old equation that we have already discussed in the previous example. So new PU reactance of the generator G1 is equal to XPU old into base MVA in new divided by base MVA old. So we are having the value of XPU old, that is 0.10, and base MVA new, that is 15, and base MVA old, that is 15 for the G1. So from that, the per unit reactance of the generator 1 G1 is equal to 0.10 pu, and the generator G2, the new pu reactance of the generator G2, that is XPU old. So XPU old of this generator is 0.10. So over here, this is the value that is given in the data, means the diagram of the example, and it is multiplied with the base MVA new, that is 15 that we have selected, and the base MVA old of the generator G2 is 10. So after solving this, we are having the value of new pu reactance of the generator G2 is 0.15 pu. Now let us solve the per unit reactance for the transformer T. So the new pu reactance of the transformer T is equal to, this is the value of the XPU old, that is given over here, that is 0.06. So 0.06 is over here, and the new MVA to the old, so 15 by 15, so T is equal to 0.06 pu. So from the above data, the reactance diagram, means the equivalent circuit that we can draw for the generator G1 and G2, the per unit reactances that we have calculated, that is J0.1, and the second reactance that we have calculated from the previous slide, that is J0.15, and this is the reactance of the transmission, that is 0.06. Now over here, the 0.06 is not printed over here, and this is the point where we are considering the effect of fault. So XTH means the Thevenin's reactance, equivalent reactance XTH at point F. So that is J0.06 is, which is in series with these two parallel reactances. So J0.1 in parallel J0.15. So after solving this, we'll have the XTH, that is 0.12 J0.12 pu, and the field current IF is equal to we'll have the V by R. So over here, the resistance is shown over here in terms of the reactances. So the XTH that we have already calculated, the combined reactance of this circuit is J0.12. So IF is equal to minus J8.33. So this is the fault current of this given system. Now the base current from the value of the total MVA rating. So IB is equal to 15 into 1000. So 15 is the new base MVA rating that we have selected, and root 3 multiplied with the kV rating, that is 11. So IB is equal to 787.3 ampere. The actual fault current is IFPU into IB. So that is IFPU is 8.33 that we have calculated from the previous slide, that is shown in the previous slide, and IB is 787.3. So after multiplying these two values, we'll have the actual fault current value, that is 655.8.20 ampere. So it can be right, that is 6.558 kilo ampere also. So this is how we can solve the example related to the per unit reactance of the given system. Now let us discuss the example number 4 related to the given topic. So over here, the synchronous generator is shown over here. This is the synchronous generator, and which is supplying power to this motor, and in between we have the T1, and then transmission line, then T2, and then bus bar, and then we have the motor, and this is the point at which we are considering the effect of fault. So a synchronous generator and a synchronous motor means each rated having 25 MVA, which is given over here. It is not written over here. 25 MVA, 11 kV, having 15% of sub transient reactance, which are connected through the transformer, a line shown which is in figure. So this is the line through which the through which the generator and motor, which are driving the power, generator is driving power to the motor. So the transformer are rated 25 MVA. This is the transformer is having base MVA, that is 25 MVA, 11 by 66. So this is the step up transformer, which is stepping up 11 kV to 66, and then 66 kV to 11 kV stepping down. So this is the step down transformer with leakage reactance of 10%, having both, means 10% leakage reactance of the both of the transformer. So the line has the reactance of 10%, so this is also shown over here, and the base MVA that is 25 MVA. So 25 MVA 66 kV is given over here. So the motor is drawing 15 megawatt at 0.8 power factor leading, and the terminal voltage of this transmission system is 10.6 kV when a symmetrical three-phase fault occur at this point at motor terminal. So find out the sub-transient current in the generator motor and at a fault at the point where the fault take place. So let us solve this. So choose a base MVA that we have already discussed, that we can take the highest value of the MVA rating, that is 25 MVA. So 11 kV is the base kV. So all the reactances which are given in proper base. So the load voltage in PU is equal to that. This is the given for the particular transmission system, that is 10.60 divided by 11. This is the base kV rating that we have selected, that is 0.9636 at angle theta PU, and load MVA, that is P by cos phi. So the means the active power, or the we can say value of the power that is given, it is 15 divided by 0.8, so that's why the load MVA will be 18.75 MVA. So load MVA in PU will be 18.75 divided by its base MVA, so that value will be converted into the PU, so that is 0.75 PU. Now load current in per unit, that is IL per unit, is equal to load MVA per unit divided by the load voltage per unit. So load MVA per unit that we have, that is 0.75, and the load voltage per unit, that is 0.9636. So after putting this value, we will have the value of ILPU, that is 0.7783. So the power factor is 0.8 leading, so power factor angle, so we can write cos phi is equal to 0.8. So phi is equal to cos inverse of 0.8 is 36.9 degree. So from that we will have the phi is equal to 36.9. So here is the leading power factor, so cos phi is equal to positive VE. So IL per unit is the 0.7783 at angle 36.9. so that we have calculated from this the previous slide. Now voltage behind the subtransient reactance generator. So we are having the equation from the generator for the generator is EG is equal to VT plus IL XD. So this is the loss of the generator, this is the terminal voltage means output, and this is the generator generator EMF. So E double dash G is equal to VT plus IL XD, that we have already, this is the equation that we can form from the phasor diagram of the synchronous generator, and that we have already discussed, that EG is equal to VT plus IL XD. So VT is the terminal voltage that we have already calculated, that is 0.9636 at angle 0, and the value of IL is 0.45, and the XD that we have calculated, that is 0.7783 at angle 36.9. So sorry, the value of the IL is 0.7783 at angle 36.9, and this is the value of XD that is given for the system is 1.5, and from that the value of EG is equal to means the EMF of the generator is 0.7536 plus 0.28 pu. Now voltage behind subtransient reactance, so EM, so for the motor is the equation is VT minus ILXD. So EM double dash is equal to VT minus ILXD double dash. So VT is equal to 0.9636 at angle 0, that we have already calculated, and the value of IL is 0.7783 at angle 36.9 degree, and the IL is 0.15. So EM is equal to 1.0336 plus J 0.0933 pu. So after that we will have the equivalent circuit, that is the generator, after the generator having the generator its own reactance, that is J 0.15, and then after we have the transformer T1, then after we have the transmission line, then after we have the transformer T2, then we have the point where we are considering the effect of fault. This is the output voltage, and then after we have the motor, and motor is having its own reactance. So this is how, after solving solving all the reactances, we can draw the equivalent circuit of the given system. The pre-fault equivalent circuit will be this, and the circuit under fault condition. So this is the point where the fault take place. So this is the line from which the fault will be grounded, and that will be connected to the EG. So IG double dash is the EG double dash divided by X double dash total from the generator to the fault. So this is the value that we have already calculated. So 0.7536 plus J 0.2800, that is EG double dash, and X double dash total that we have the 0.45 from this. So 0.15 plus 0.30, so this both are in series, that's why the total reactance is 0.45. so then after, the IG is equal to 0.6226 minus J 1.6746 per unit. So from that, this is the circuit current under fault condition for the generator. Then after, we can calculate for the motor as well. So I double dash M is equal to EM double dash divided by X double dash total from the motor to the fault. So the EM double dash that we have already calculated 1.0336 minus 0.0933, and the reactance which offered by the system over here after fault point, so that is 0.15. so after solving this, we will have the I double dash M, that is minus 0.6226 minus J 6.8906 per unit. So total fault current IF is equal to IG double dash plus IM double dash, so that will be minus J 8.5653. so this is how we can solve the example related to the given system. Now then after, we can calculate the base current of the given system, generator or motor. So that we have already 25 base MVA, so 25 into 1000, and the base kVA, that is 11. So from that, the base current is 1312.2 ampere. So IG actual is 1312.2 into 0.6226 minus J 1.6746. this is the value that we have calculated. From that, IG double dash will be 816.4 minus J 2197.4 ampere. So this is the actual the current which is drawn by the system when the fault will take place, where the IM double dash actual is 1312.2. it is multiplied with the IM double dash, that is 0.6226 minus J 6.8906. so the IM actual will be minus 816.2 minus J 9041.8 ampere. So when we means add these two terms, means IG double dash actual and IM double dash actual, so we will have the actual value of the fault current IF is equal to IG double dash plus IM double dash, that is minus J 11,239 ampere. so this is the current will transfer to the system where the fault will take place at the point where the motor is connected in the system. Now let us discuss the example number 5 to the given system. So consider the 3 bus system which is shown in over here. So this is the bus number 1, 2 and 3. With bus number 1 and 2, we have the generator G1 and G2. Then after, we have the transformer T1 and T2. Both are step up transformer from 11 to 110 kV, and this is the line reactances which are means line impedances which are mentioned over here, and this is the point 3 which means bus number 3 where we are considering the effect of fault. So the generator which are having 100 MVA with a transient reactances of 10% each, so both are having same reactances, transient reactances, and both the transformers are 100 MVA with leakage reactance of 5%. so the reactance of each line to the base of 100 MVA to the 110 kV is 10%. so obtain the value of fault current for 3-phase solid short circuit on bus number 3. So we are considering the fault over here. Assure pre-fault voltage to be 1.0 pu and the pre-fault current to be 0. So this is the data which is given to calculate the example related to the given system. So let us solve this given system. So first of all, this is the equivalent diagram of the given system. So all the reactances and the impedances means which are given over here, admittances of the line. So it is converted like this. So this is the equivalent diagram of the given system. So the base MVA that we have selected, that is 100 MVA, which is given. The base voltage for LT side of the transformer, that is 11. So this is step up transformer in both the cases, 11 to 110. So base voltage for the LT side of the transformer, that is 110, because we are having the transformer step up after the generator, that is 11 to 110, and base voltage for the generator, that is 11 kV, and per unit reactance of the G1, that is 0.1 pu, and the per unit reactance of the G2, that is 0.1 pu. So then after we can calculate the per unit reactance of the transformer. This is the equation that we have already used, new base to the old into its reactance. So this is 0.05 into 11 by 11 square into 100 by 100. So that is j 0.05. So this is how we can calculate all the per unit reactance of T1, T2, then line 1 2, then line 1 3, and line 2 2 3. So this are the pu reactances of the given system. And then after, the reactance diagram means equivalent reactance diagram that we can redraw after solving this pu reactances of the given system. So that is redrawn like this. So let us calculate that. Reducing this diagram means over here we are having series and parallel connection of the transform means the reactances. So the equivalent reactance will be 1 at angle 0, j 0.1245. So reducing this diagram, delta to star conversion, that we have already discussed how to convert delta to star. Now series parallel combination simplification, we will have this equivalent circuit. Then fault MVA, that will be 1 divided by that we have considered, that 1 pu for the given system, divided by 0.1245. So that will be, the fault MVA will be 803.2 MVA, and the fault current is 1 divided by 0.1245, that is 8.032 per unit. So the base current, that is 100, that we have taken into 10 raised to 6 into divided by root 3 into the base kVA, that is for the secondary side 110 into 10 raised to 3. So the base current is 524.86 ampere, and the fault current is the total fault current is 8.032 multiplied with 524.86. So total fault current of the given system, where the fault is being taken place, that is 4215.7 ampere. Now after this, all the example, you will have the assignment questions in terms of the example. So these are the examples. You can take the snap of this slide and you solve this example related to the chapter. And this type of examples are frequently asked in your GTU exam. So please calculate it carefully, and if you have any query and any doubt related to this examples, feel free to call me anytime. Also we can solve your doubts and queries in our doubt solving session. So the instructions which are related to this assignment question, which are written next to this slide. So please read it carefully, and if you have any further query and any doubt related to this topic, feel free to call me anytime. And also we can solve your queries and doubt related to this topic in our doubt solving session. So please, you can take the snap of this instruction also. And thank you very much, student. Thank you very much all. Jai Swaminarayan.